mission critical and decentralized infrastructure. So just to give you a bit of an idea what's Condair. So Condair used to be called actually Nortec in North America, in Canada and US. So Condair is actually 70 years old. So it's a company that was founded in Switzerland in the 48 after the war. And then through the 70 years of history, we acquired many companies worldwide. In the 80s, we also acquired Nortec in Canada, which was rebranded to Condair 2 years ago. But you can see we have a long history, and mostly we have been a humidification company. And in the last, let's say, 20 years, we're also a lot in the adiabatic cooling. So you can see on the map, so we are present in 21 countries right now directly with our own office sales. We also have 6 R&D and 6 production sites around the world. So for North America, our factory and main offices are actually in Ottawa, so in Ontario. And we also have an office and a warehouse and service center in Sturtevant, Wisconsin. We also have in Mexico. And then we have an R&D center also in Canada, where we do a lot of development new products. And then we have also another ones in Europe and China. So to give a bit of, like I said, Condair is primarily a humidification company, but we also do a lot of adiabatic cooling, and adiabatic cooling is connected, let's say, with the adiabatic humidification. So it's the same principle, right? So typically in humidification, you have isothermal, like steam, so when you boil the water, or you have adiabatic humidification. Adiabatic humidification can be both atomization, like droplets, or it can be evaporation, like media systems. And this is what we're going to focus today on our applications, is mostly media systems, because that's what's typically used in data center applications and in data centers. So like I said, so the difference between adiabatic and isothermal, so like I said, isothermal is typically steam, so you have to boil. It can be gas, electrical, there are different methods, but essentially you boil the water and you get the steam. While adiabatic, when you spray the water or you evaporate the water in the air, the energy comes from the air. So you get your adiabatic cooling. So you can see in the psychometric chart, when you look on the process, so the red line is a typical steam process. So it goes up with the same temperature. While adiabatic cooling, you can see the blue line, it goes from in the constant enthalpy. So when you evaporate water on the air, you also get your cooling. So to give a quick example, for example, if you have 20,000 CFM and a load of 200 pounds, in this case is humidity, but will be similar for cooling. With the electrics, for example, you get 75 kilowatts to evaporate 200 pounds an hour. While if you have, for example, an ME system, you can see on the picture below, it's only around 300 watts. And you can get up to 2,200 pounds per hour. And you can see with your adiabatic system for 200 pounds an hour, you'll get a delta T of 10 degrees Fahrenheit. So you get also an adiabatic cooling. So we have lots of products in the adiabatic range. So like I said, they're primarily going to focus on the adiabatic products. So you can see we have on the left, we have media systems, we have spray systems. We also have hybrid systems, that's mostly ceramic with the atomization system. Then we have in-space systems, you can see high pressure, compressed air, rotary. Then we also have small applications for in-space like ultrasonic, mobile evaporators, and a ceiling humidifier, also evaporative. So you can see we have different types of applications for very big loads to very small loads. And we also have an in-house water treatment system for very small systems for reverse osmosis to very large systems for water treatment. So one of the things also we want to discuss in this webinar is in the recent years, we see a lot of blockchain applications. So most people are familiar with, let's say, Bitcoin. So that's a public ledger blockchain. So that's what's always in the news. But there are lots of companies that are also doing private blockchain networks these days. And it's kind of a recent, I'll say 10 years when the first paper came out on this. But it's basically a system where you add blocks to a chain so you can have all this validation on your supply chain or transactions, etc. So what we are seeing these days, especially in the currencies, because there's something called a proof of work, where they always need to solve a mathematical problem to validate the transaction, there is a big demand for power and energy. So we are seeing these days across North America, lots of miners companies, and to give an idea, some people are saying it's soon going to be half of the energy consumption of all data centers in the world. So what they do, so like I said, is a new digital ecosystem. So there is a big debate these days about the energy they consume. So it's very consume intensive because of all the validation to fix the double spending issue, right? So what we are seeing is, because of the value of the currencies also go up and down, there is a big focus also on the cost on mining. So most of the cost is still the electrical one for the equipment, but there is also a cost of the cooling of those data centers. So most of these data centers or mining facilities are considered tier one. So they are very basic. So they don't care much about redundancy or other aspects like tier 3 and 4 data centers. But you see more and more that are being built primarily in areas like where it's cheap energy and like also get free cooling in the winter, like northern Canada, northern Europe, so they can get free cooling. But one of the issues also is if you bring a lot of free cooling in the winter, then you need to humidify that air. So that's where Condair can help. We can provide solutions both for cooling in like places like Arizona, for example, in the summer, or if you have a strategy to free cooling in the winter, you can also mix with our systems to humidify that recirculation. One of the things, like I say, you can see, for example, some of the typical equipment for mining for digital currencies. If you see the requirements, they are quite broad. So they go from 10 to 90% RH, 23 to 104. So they are typical, not as critical as a colo center or hyperscale data center. So you can have a big range, but still the temperature you can see is 23 to 104. So you will need cooling, of course, because all these minor facilities, they'll have a huge heat load. So like I said, that's where you can help. So we can have both our evaporative systems or our humidification solutions for cooling in the summer, or if you have like free cooling in cold areas, then you need to humidify because it will probably even be less than 10% RH, and then you have a lot of static inside your data center. So like I say, one of the big issues, and like I say, you can see in this graph from BBC, right now just Bitcoin is almost half, or actually more than half of all data centers worldwide for electrical in terawatts hour. And the reason, like I say, is because the way blockchains, and some of them were designed on the base code, they are based on the proof of work, right? So it means every time someone does a transaction, the only way to validate that transaction to make sure you don't do the same transaction different times is to solve that mathematical issue. And what the miners do all over the world is they basically compete. So every time there is a transaction, they'll compete with each other, and the first one to find a solution to that problem gets the rewards from Bitcoin, for example. So what happens is the more the chain is growing, the Bitcoin blockchain, the more difficult the problems is. So the more power you need to fix this issue. And if you want to be competitive, so if you want to find the solution before the other miners, you need to increase and increase more your power. That's why you are seeing Bitcoin, the data centers or data mining facilities, they keep raising every 6 months, because if they don't grow in processing power, then they will not be able to solve money transactions, and then it's not competitive anymore for that. Of course, it might change in the future. So there are some people talking about proof of concept these days, unlike proof of work. But right now and in the next years, probably the blockchains, if it's a public ledger, will have proof of work principles. If it's private, it's different, because then you don't have to compete. But you also need a big data centers if you have big private blockchains also. Like, for example, supermarket chains are doing these days, so they can transact, see from the farmer up to the supermarket, they can quickly see all the process with the products. So now I'll pass to my colleague, Will, for a talk about the data centers.
Perfect. Thanks, Nuno. So, as Nuno had mentioned, the computing power needed to complete these blockchain transactions is huge. And the facilities that are being built for these mining and transaction computing is very similar to effectively a high density data center. So year-round cooling load effectively, and then also depending on the location of those facilities, potentially a need to maintain that minimum humidity level that's required for those mining servers. But in terms of data centers in general, Bitcoin facilities are probably going to be more like your traditional hyperscale, where these are typically large facilities with a wider operating range in terms of temperature and humidity. Nuno talked about the amount of energy that's required here. And then we'll talk about the water consumption as well on some of these adiabatic systems. But because of the scale of these types of systems, even a 1% efficiency gain on the cooling side can make a really big difference in overall operating costs for these facilities. Even though a lot of that power is still required for the computing, we can certainly help improve efficiencies on the cooling side as well. So that's on the hyperscale side. In terms of data centers, on the colo side, we do see the use of evaporative cooling as well. It is fairly limited depending on which colo provider we're talking about. Typically, evaporative cooling systems are going to be used on the larger scale sites where they can really take advantage of the scalability and the cooling effects there. On the edge side, in terms of data centers, these are typically smaller facilities, small rooms or closets, and just based on the load and the requirement for cooling and humidification, we don't really see a lot of evaporative cooling being used there. So on the data center side, primarily hyperscale and co-location facilities are really where we're seeing the expanse in terms of evaporative cooling systems being used. So, Nuno talked about the power. When we talk about data centers and even some of these mining facilities, power usage effectiveness is effectively the total facility energy use divided by the IT energy use. And, as you can see by the graph there, equipment has come a really long way in terms of reducing that PUE, in terms of energy usage, getting that down to as low as about 1.5, depending on the data center. The other side of that we're seeing being focused on more now is actually water consumption. So, as the West Coast in the US has experienced droughts in recent years, water and scarcity of water is becoming more of a concern. So when we start talking about using water for evaporative cooling, the question always comes up, well, how much water are we actually using? How much is going down to drain? So that is certainly something that we're seeing being looked at a lot closer now, even more so than the actual energy usage in some cases. So in terms of our systems, we do have ways to try and optimize that water usage, and I'll talk about that a little bit later on when we start looking at the evaporative systems as well.
Okay, thank you, Will. So now we'll focus primarily on our ME series. So our ME series is our evaporative system series, so we'll not focus on the other applications. So if you have questions about other applications like smaller cooling or humidification, you can contact me or Will. But today we'll focus primarily on our media systems because that's typically what we use in the data applications. So when you install evaporative systems, there are, let's say, 3 different ways you can install. So you can have a direct evaporative cooling, so you humidify or you cool the air, so you increase both your humidity and you decrease your temperature, and you supply directly to the room. You can also have indirect evaporative cooling, where you're gonna cool the outside air, and then you have heat recovery that will cool the return air and send it back to the room. So this way, the benefit is you don't humidify the air, you just cool the air. So if you don't want to increase your humidity, but you still want to use the benefits of adiabatic cooling, you can also use this type of application. Another application you can see here is if you put your evap system in your return, you can also cool as much as you can because you're exhausting that air, so you don't really care. You can go up to 95, 96%, and then use heat recovery for sensible heat recovery to cool down the incoming air that you supply to your data center in this case. So like you can see, there are different types of application you can use. Depends also if you want sensible and latent or only sensible cooling. So like I said, we have our ME system. So it's a system that uses glass fiber. media applications. So you can have we have two types of systems, let's say. So we have this picture you can see on with our technician. That's a recirculation system. So we have a hydraulic module that recirculates the water through the system. Or you also have systems like direct feed that just flows through the system and goes directly to drain after the tank. So these will be our standard systems. We also have custom systems that William will talk after, that we do for specific jobs and customers. One of the neat things of our system also you can see is the media. So the media you can see on the right, it's always in a stainless steel frame with the interlock mechanism. And the way we do this is it's easier to assemble, and also there is no risk of collapsing over time, especially if it's a large XL system. So like I said, we have different types of media. So we have 4, 6, 8-inch media. So we have also different fluid angles, 30, 30, 45, 15, depending on the efficiency you want. It's a UL 900 media. Also, our system is very low energy consumption, like I said before, less than 300 watts. It's all stainless steel, the tank, the uprights, the cassettes. So all the metal in the system is stainless steel. The hydraulic modules you can install inside or outside your duct. You can see also in the picture. And we also have different hygiene features like drain cycles. We have submerged UV on the tanks, inline UVs. So all the blue mold you can see in the hydraulic is actually also antimicrobial plastic. So we implemented different hygiene features also to avoid the risk of development of biofilm during the application. So you can see the picture. So also our standard systems, they all come with BMS, BACnet, Modbus, IP, MSTP. So you can see in this case was a plenum installation. You can see the blue light, it's actually the UV below the tank. And in this case, you see the hydraulic was installed outside the plenum. So like I said, standard sizes around 14 feet wide by 13 feet high, but then we do custom solutions per customization. So it's a very highly customizable. It's possible to customize this product, and like other products that are it's difficult to change. With media systems, we can actually tailor the system to specific customers based on their demands. So, like I said, one of the nice features of our ME series is the hydraulic module. So you can see we actually have individual pumps instead of a single pump with the stage. So each pump will actually control one stage of media. So why is that? It's for better control and also for redundancy. So if one fails, the other columns of media, they still work. So these are DC pumps. They are very, very quiet. So, and they should last like 50,000 hours. So they'll last many, many years. So that's one of the neat applications is, like I said, when you look back on, so each column of media you can see in this picture, sorry, you'll have one pump to control individually that column. Then we also have conductivity sensor and temperature sensor, and that's for hygiene and also for the water. When the water conductivity is too high, we typically drain the system and then replace with fresh water. Like I said, media we use glass fiber is UL 900. Our system also, the standard system is UL 998. So you can install in a plenum or an air duct. We have 4, 6, and 8-inch media, 75 to 95% effectiveness. Also, our media has a silver coating, so for hygiene reasons to avoid the bacterial growth. So we submerge them when we manufacture the media. We put the silver ion coating on the media. Like I said, we have 30-30 fluid, so that's a high efficiency media, and then we have for cooling also 45-15 media. We also sell only media for some customers. If they only want, we only provide the media, and then they build their own systems. So now I'll pass to my colleague William, and he'll talk about custom solutions that we do in the Condair.
Perfect. Thanks, Nuno. So yeah, as Nuno mentioned, the ME is our standard product, but we fully understand that that clients and end users and designers may have a specific set of requirements, specific set of components, even a specific control scheme that they like to operate, these direct evaporative systems or adiabatic systems too. So on one side we have our standard off-the-shelf product offering, which is the ME, but we do also have the ability to customize and tailor a solution depending on the specification or the requirements that are needed by the end user. So we have a number of examples here that I'll take you through just to give you an idea of some of the different requirements that we see on these large scale applications. So one, of course, is what we call an OEM unit. So this is more similar to your traditional evaporative cooler or swamp cooler. But in this case, the requirements are, we have a third-party controls contractor, we have a set control scheme that we need to operate to. We do not want to use the Condair integrated controller with all of our, logic in terms of controlling the individual components, the water management, the hygiene. They just want the evaporative module with all the components that they can control based on their control scheme. So with this, what we've designed is effectively an OEM unit with a more traditional single submerged pump. And we have the ability to kind of tailor this if they need stage control, if they just want on-off control as well. So the really great thing about these types of systems compared to your off-the-shelf, standard steam humidification systems is these are very, very scalable and very, very customizable as well. So that's just one of the options that we have available if you've got a client that doesn't want the full package with integrated controls. So that is something that we do have available there. Next slide, Nuno. Again, very similar. This is also an OEM unit, but one of the requirements here was to actually integrate a bypass damper for control of the leaving air conditions. So one of the ways that we control or typically control our ME system is just by turning on individual stages of pumps. So on a large unit, we can have up to 7 stages of individual control. If a client is looking to use bypass control and just operate the unit as on-off, and using bypass air and mixed air downstream to control the leaving air conditions, we can do that as well. This client in particular had a requirement to integrate a bypass damper in between 2 banks of evaporative media. So that's effectively what we've done here is designed a single system with 1 pump, 1 set of controls, 1 sump, but 2 banks of media with a 24-inch section left in the middle where the client could integrate in their own bypass damper for additional humidification or cooling control. Very similar here in terms of the previous design where the client was using bypass dampers to control the leaving air condition. But in this case, we were somewhat limited in terms of the amount of media that we could put in perpendicular to the airstream. So what we've done here is just put the media in on an angle to increase the free area or media area that we've got in the airstream. And that just helps us to bring the overall pressure drop down, the velocity on the media down, and increase our evaporation efficiency. So really just trying to get more media into the airstream by putting it in on an angle versus just perpendicular to the airstream. This is another interesting one here in terms of a series design. So this client was more concerned about air stratification within the airstream on a fairly large unit. So what we've done here is actually just put 2 banks of media, 1 downstream of the other. So in this case, we have a 4-inch bank upstream. Directly downstream from that, on the same frame, same module, we have a 6-inch bank of media. And the way that this unit was controlled initially was stage 1 was the 4-inch bank on by itself. Stage 2 was the 6-inch bank on by itself. And then stage 3, of course, would be stage 4, the 4-inch bank and the 6-inch bank on at the same time. We took that actually 1 step further and actually optimized the staging on the 4-inch bank just to give them a bit more modulation on the low end. So you can see we actually lined up the individual columns with the fan arrays that they had. So we could actually turn on stage 1 as the smaller columns on the 4-inch bank, and then stage 2 would actually be the larger columns, just to give a bit more modulation on the low end or controllability on the low end. But in terms of air stratification with that type of setup, I think on this, which was a fairly wide system, we had less than a 1 to 2 degree temperature difference from the top corner to the bottom corner on the opposite side. So very effective in terms of eliminating stratification in the airstream. And then again, just to show you the scalability of these types of systems, this is a large hyperscale design that we supplied in northern Sweden. You guys may have seen this before, but effectively this was located in northern Sweden, so they were actually able to take advantage of the colder outside air temperatures most of the year without actually needing any type of additional mechanical cooling. But because that outside air was coming in very, very cold, and they were mixing that with the warmer return air from the data hall, the humidity actually dropped below 5% in some cases. So the adiabatic systems that we put in were actually primarily to bring the humidity levels back up to about a 20% minimum there. So I think the next slide shows that fairly well in terms of the setup. This was a fairly large plenum design, so not dedicated air handlers like you would traditionally see. But in this case, air is moving from the right to the left. We're drawing that mixed air through the evap cooler, through the fan section, and that's being supplied directly into the white space. So just to give you an idea of the scalability of these types of applications and systems. And then the other picture that we're looking at here is actually the previous phase of the same facility where we actually supplied our atomizing high pressure systems, where we're actively spraying water into the airstream at about 1,000 PSI. One of the big differences here was the water quality requirement. So anytime we spray water or atomize water into the air, we have to make sure that we are pulling those minerals out, anything that is in that water, before we spray that into the airstream. Otherwise, those minerals will precipitate out as white dust. They'll clog filters. They could potentially damage sensitive equipment downstream. So in this case, because we were atomizing the water, we actually had to supply a fairly large water treatment system as well. And if you recall, when we spoke about this earlier, what we're seeing now is actually a focus on water consumption. So right off the bat, you're penalized by going through an RO system. You're going to have 30 to 40% of that water going into the RO system sent directly to drain, just because that's how RO systems work in terms of pulling minerals out. We also have the inefficiencies, or some inefficiencies, on the atomizing system as well. So the water consumption on these types of systems where we're spraying water is significantly higher in most cases than a more traditional direct evaporative system or media system, which is one of the reasons I think that we are seeing a shift back towards those types of systems, because water consumption is being looked at a lot closer now. So with that, we'll jump right into water quality here, and that's something fairly new that we've started looking at because of this request for maximizing the efficiencies on the water side for these types of systems. So as I'd mentioned, one of the big benefits to using a direct evaporative media system is that water does not need to be treated. So you don't have to go through an RO system, you don't have to go through a DI system, so you don't have any incurred water losses right off the bat. The only quality that we require is a minimum drinking water quality for these types of systems. But as we know, water quality can also vary by location, as well as potentially throughout the year, depending on where the municipality is pulling water at that time. So it is fairly tricky to optimize based on a specific water quality, as that could potentially change. But if we have an idea of what that water quality is at different times of the year, we can run different calculations to try and optimize that. But really, what we're looking at here is optimizing or finding a balance between the water that we're draining out of the system and media life effectively, or scaling on that media. So what we're primarily concerned about here is water hardness. The water hardness is primarily coming from dissolved calcium and magnesium that's in that supply water. As we boil that water, or in this case, as we evaporate it into the air, that hardness will concentrate, and once it hits a specific concentration, will begin precipitating out in different forms. In general, what we see that form as is scale formation or buildup on the evaporative pads themselves. And what that can do is actually decrease efficiency, because we lose surface area on the media, and we also see potentially an increase in pressure drop, because that scale starts blocking off some of the flute configurations that we have on the pads themselves that allow the air to pass through. So the solubility of the calcium and the magnesium are dependent on a few different factors. So dissolved CO2 in the water, as well as pH and the water temperature as well. So depending on where you are, we've got a European scale for hardness. Here in North America, we typically look at hardness as ppm of calcium carbonate. So, looking at the low end, soft water would typically be 0 to 60, or if you're looking at TDS, 0 to 150 milligrams per liter. And then on the extremely hard side, we're looking at a hardness of over 350 and a TDS over about 850. So, we've seen a very large difference in terms of water quality throughout the US. So ideally, if we are looking at a specific site or specific location, a water sample directly from the install location or site would be more beneficial than getting that a general water quality analysis from the municipality. But certainly any additional information we have on water quality can help us to optimize these types of systems. So just to give you an idea here in terms of maximizing the water quality or water efficiency, what we do is effectively try and maximize the number of COCs or cycles of concentration inside of the DEC system. So the cycle of concentration is effectively the TDS in the sump divided by the TDS of the supply water. So how many times can we actually concentrate that water up before we need to drain that water out of the system? So typically in an evap system, we would have a blowdown cycle that would drain some of that concentrated water out while the inlet valve brings in fresh makeup water to maintain a specific TDS within that sump. Just to give you an idea of some of the scale buildup that we would typically see on the media if we're running on potable water, it can be as minimal as light sodium buildup if we're running on soft water. In some areas that can be lightly brushed off. But if we're looking at a harder water, potentially with more calcium, we'll see that as a harder scale that can actually block up some of these flutes. And as I'd mentioned, that would increase pressure drop and decrease efficiency on the system as well. So again, it's really just maximizing the water usage versus media life or scaling up on that media. So by knowing just a few parameters based on some of the empirical data that we've gathered throughout the years and these systems running in the field, we've developed a way to try and calculate or optimize the cycles of concentration to determine when a blowdown should occur to try and minimize scale buildup on that media and try and extend the life on the media while minimizing water consumption. By no means does this guarantee no scale formation on the media. Again, really due to potentially changing water qualities or changing in terms of the operation of the system throughout the year. But it does give us a very, very good starting point for looking at how we can optimize that water and setting up the system initially. So when we look at this, really all we need to know to do this calculation is the system configuration. So that's going to be your unit size, the peak evaporation rate, which is typically what we use to design the performance of the system around, and then the design air conditions. And then on the water quality side, what we would typically be asking for is the supply water temperature, the hardness, and the pH going into the system. Just to give you an idea there, pH range, we typically try and keep between 6 and 8. Ideally, the closer to 6 we are, the better we are in terms of running a higher COC or higher water efficiency at that point. And then in terms of temperature, the colder the water, the better. That helps us operate in a non-scaling mode with a maximum temperature of about 24 degrees Celsius, primarily just for hygiene reasons, because as we get higher than that, it really starts to promote the growth of bacteria in the water system. So just a few things to keep in mind. If you do have a site where you would like to look at trying to optimize this and look at the media life and water quality, if you have a sample of the water, we can run a sample at a local lab in Ottawa, or if you have a water analysis that's already been done with those parameters that we are looking for, just send those to us and we can run those calculations and give you a pretty good idea of what the maximum COC would be for that system, or potentially what the media life would be on that system if we're running on a fairly hard water system. And then as Nuno mentioned, primarily we focus today on our direct evaporative systems because those are really what we're seeing being used in these large facilities. But we do also have a full range of cold water adiabatic technologies. So as Nuno mentioned, we have the DL, which is a low pressure atomizing system with a ceramic media downstream. We have your more traditional high pressure atomizing systems. And then for the smaller computer rooms or server rooms, we actually do have standalone systems. So for example, the US, which is our ultrasonic series that maxes out at about 40 pounds an hour. Really ideal for small computer rooms, small server rooms, where you just need a minimal amount of humidity and potentially some cooling as well. And then a new product for us this year as well is what we're calling the TE series, which is a small ceiling mounted humidifier, which is an evaporative system, but fits within a drop ceiling space. So if we're limited on install space, or if you don't have a ducted air system where we can retrofit a larger cold water system, that might be a perfect fit for that. So, I mean, just to summarize here, I think the benefits of adiabatic cooling technologies for these types of applications are evident. There's huge energy benefits as well as a fairly good payback in terms of these larger facilities. On the other side of that, certainly the humidity range or the optimal humidity range for human and health is between 40 and 60%. So the other benefit here is 40 to 60% can help the employees, the occupants of the facility as well. And then, of course, from the Condair side, we've got a lot of experience with these types of applications. Certainly any questions that you have on any of this stuff that we've talked about, or any application-specific questions, certainly reach out to your local rep or even us directly at the factory, and we'd be happy to help you out with that. So I think we've got our contact info down there as well. If you do have any other follow-up questions or would like any additional information on anything that we've talked about here, feel free to send us an email and we can certainly help you with that.
Thank you, Will. So thank you everyone for joining. So if you have any questions now, you can actually write them on the chat. And so in your application, your webinar application, there is a chat where you can make your questions based on anything we presented today. Just expand this just a minute. Okay. Someone is asking if we expect digital currencies to be also developed in North America. So yeah, so most of it is still in China these days, so because of the energy costs, but we are seeing more and more also in the North America, even in Canada. So we expect to grow, but still China is more than half of the mining these days is in China. And then someone is asking if it's sustainable. So that's the question. I think nobody even knows the answer. So right now, many people say it's not sustainable, but eventually what might happen is when you start to mine a lot, then the big players will adopt and they'll use like big hyperscale, so which will reduce, or they'll find another equipment to mine. But right now, that's one of the fears, is it's going to become very unsustainable because of the rising energy costs for validation. So this one is for you, Will. Is drift eliminators used on our systems?
Yeah, so we would typically supply a drift eliminator or droplet separator in applications where we are running at a higher media velocity. So without a droplet separator, we can typically run up to about 690 feet through the system. Or through the media. In terms of a design aspect, that is probably an upstream air velocity of about 450 to 500 feet per minute, just because we do have on our deck systems the sumps and some of the metal work, and we actually take into account in our velocity calculations the sheet thickness of the media and the glue as well. So we do lose a little bit of area there, which is why we would typically see an increase in velocity from your duct air velocity to media velocity. but up to about 690 feet per minute through the media, we would not require a drift eliminator. Above 690 up to about 890 is when we would start requiring or recommending a droplet separator drift eliminator. The other aspect to keep in mind there is, of course, we are assuming that we have somewhat laminar airflow. We have seen a lot of applications, depending on the type of fan that's being used as well, where we have uneven airflow to the face of the evaporative system. So in that case, if we have high velocity areas, we may still need a drift eliminator, even though the design says that we are under 690 feet per minute. So that's just something to keep in mind there.
Okay, so someone is asking about the presentation. So yeah, the presentation and recording will be shared with all the participants. And someone is also asking about the RO options. So for RO, we have from very small systems, from like, you can use like 50 pounds an hour of water up to 5,000 pounds an hour. So we do modular systems. So you can have just a very small RO for one small in-space unit, or you can actually have a large RO system for multiple ME systems, for example. Someone is asking, with RO water wheel, what will be the typical age or average age of the media if they use RO water?
So our general rule of thumb is, if you're running on potable water, we would typically see 3 to 5 years on the media itself. Running RO water, we may see that go from up to 5 to 7 years, but again, that really depends on the quality of the RO water compared to the quality of the potable water as well. But we do typically see 1 to 2 year increase in terms of media life. But if depending on your location, if you are running on a fairly clean water supply from the municipality, we've seen applications that have gotten 7 years on the media as well, with a very minimal increase in pressure drop or scaling. One thing I will point out there in terms of our design as well, to help mitigate the scaling on the media, is we typically design the water flow rates based on a peak evaporation rate plus some excess. So generally, we design for a peak evaporation rate, say 500 pounds an hour. We would typically flow 1,500 pounds an hour, so 2 to 3 times the peak evaporation rate, just to ensure that we have sufficient water going over that media to prevent large scale buildup on those pads.
Okay, so someone is also asking the sealing unit, the evaporative sealing, what types of water it uses. So the sealing unit, the evaporative, the new one, it only uses like normal city water. So you cannot use RO or DI water. Soft water is also fine. So I'll say you can only use normal city water or soft water. So someone is asking for a small room application with no ducts. So if you have no ducts and if the load is not that small, you can use the ultrasonic humidifier that is in space, or the sealing unit is also in space. So those units are typical units you're going to use when you don't have any duct, so you still want to add humidification to the room. So that's probably your only option. Does the RO attack the glue used on EME series? So no, typically not. So we have many sites with RO water. You might have some issue if you have like ultra pure water, like 80 mega ohm water. Then if it's like a DI water, then yes, it can start to eat the glue on the ME series. But if it's normal RO water, that's 5 microsiemens, for example, we don't see typically any issue over the years. What else? Let me see. Yeah, if you are interested in some custom solutions, like Will was saying, so it will not be in our website, so you need to contact one of us from Condair, and then we can discuss how to move forward and how to design it. But typically in our website, in our literature, the only systems you're going to see is our standard systems like DME, being the recirculation version or the direct feed version. Yeah, someone is asking also about case studies. So in our website, if you go to condair.com, you can find actually some papers about some evaporative cooling applications we did also. And I think that's all the questions. So we're almost at the end of our time, actually. So if there is no other questions, thank you for your attendance. Like Will and I was saying, if you have any questions or you want to discuss for like any product we have, just contact me or Will, and we can take it from there. And like I say, we see a lot of applications moving forward for data centers. So the world is going in that direction. So data. So if you have any case study you want to do, any project, any special applications, just contact me or Will, and then we'll help you guys designing your data center application, being for Bitcoin, for data, hyperscale, colo, edge. So we have products for any type of size of data center. Okay, and if that's all, thank you so much, guys, and I hope you have a nice day. Like I say, everyone will receive a copy of a link for the presentation and for the recording. Okay, thank you so much.
Thanks everyone for your time this afternoon. Really appreciate it. Thanks a lot. Take care.
Thanks a lot.